All right, ladies. So today what we're going to be talking about is the concept of resistance and how that affects our different values in circuits. Okay. So let's start with the basics. First of all, we are in your note packet. We're in the part that's resistance in series, parallel, and combination. We're going to go through some of the basic note pieces ahead of time together, and then you are going to be working on the rest of the packet independently. So let's start with some definitions. Resistance is the opposition to the flow of charge. And this is something that you will see real easily when you talk about this in, when we talked about it in the lab and all that kind of stuff. Because don't forget that we saw that the water didn't move as easily when they were going through the resistors. In electricity, the units of resistance is something called an ohm, whose symbol is the capital omega you see here. Okay? All right. Now, current, another thing that we've been talking a little about, is basically the rate at which charges pass a given point. Okay. The equation for it is, okay, in current, again, I. The equation is that current is the charge per time. So current has units of coulombs per second, also known as amperes, or amps for short. Voltage is the electric potential difference. And quite honestly, we're never going to say electric potential difference after today. We're just going to call it voltage, because it's easier. Right? And notice we are dropping the delta, so we're not worried about it, but we're still going to be using that as a voltage or difference. Its units, I bet you know, or should know, they're volts, which is capital V. Okay? So, moving on. When resistors are placed in blank, they come one after another, allowing only one path for which the charges can move. From your studies in the water circuit lab, you should remember that that means in series there's only one path for which they can move. The voltage across the resistors will vary with the resistance, or varies with the resistance, while the current remains the same. We should have seen that in the lab as well. And when resistors are placed in parallel, there are multiple paths on which the charges can flow. In this arrangement, the current through each branch varies based on the resistance in that branch. However, the key feature of a parallel arrangement is the fact that the voltage across each branch is the same. This is huge. This is like guaranteed question on the test. What makes parallel parallel? I really, really, really want you to know that what makes it parallel, not only are there multiple branches, but the voltage across each branch is the same. That is the key. Now, when we combine resistors, okay, you can combine them in such a way that you could replace all the resistors and get the same overall resistance. This is known as the equivalent resistance, which is what we will be working with and finding for the rest of this period. Okay. The equivalent resistance is the amount of resistance that a single resistor would need to have in order to replace all the resistors in a combination of resistors in order to draw the same total current. Okay. So basically what we're saying is this is the total or overall resistance in the circuit. When we do this, we're going to need how to figure out how to find the total resistance or equivalent resistance both in series and in parallel. So to do that, we're going to need equations. In series, where the resistors come one right after each other, it turns out that the equivalent resistance is given simply as the addition of each resistance added together. Real easy, straightforward. However, in parallel, it turns out that the overall resistance, if you have multiple resistors and giving you multiple paths, works out to decrease the overall resistance. And in this case, we say that it adds as the reciprocal, which means 1 over Req is equal to 1 over R1 plus 1 over R2 plus 1 over R3. I get this might be a little confusing at first. Once you do a couple of problems with it, you're totally going to get the hang of it. So, our examples. Okay. Given the schematic diagram below, find the equivalent resistance between A and B. And I probably should have actually marked A and B. Sorry about that. Okay, so working our solution, we would say that between A and B, we have a series combination, okay, because they're coming one right after each other. If you follow your finger along, there's only one path that they can go on. There's not multiple ways you can do this. Okay, so since they're in series, the equivalent resistance is fairly straightforward. It would be resistor 1 plus resistor 2 plus resistor 3, or 10 plus 33 plus 70. Well, 70 plus 33 is 103 plus 10 is 113 ohms, which we check as our answer. Good to go. Nice job. All right. So, assuming you don't have questions on that, we're going to move forward to example 2. And again, I accidentally did not label A and B. Okay, pardon me. And here, between A and B, what you should see is that there's actually a spot where you get a break. You have options. And when you're drawing your finger along from A, along the wire, then all of a sudden you have options. Where you have options, that's going to be your signal that you are in parallel. Okay? So in parallel, the equivalent resistance is a little bit more complicated. It's 1 over R1 plus 1 over R2, which means the equivalent resistance would be 1 over 330 plus 1 over 100, all of that as a, add those two together and then take that total and raise it to the -1 power, which I am doing on my calculator right now. So open parentheses, 1 divided by 330 plus 1 divided by 100. Don't forget your decimal points, so you get a full value. And then close parentheses, caret, -1. And that gives us 76.744186 on and on and on, which is 76.7 ohms, which agrees with our answer here. So, looking at our examples, all right, and I want you to go look back up at the top of the page, example 1. The total resistance, is it greater than, less than, or equal to each individual resistance? When in example 1, when they were in series. That's right. The total resistance is greater than each individual one. In parallel, the total resistance was 76.7 and therefore less than each individual resistor. Okay. Now that you've seen a couple of examples of how to do this, I'm going to encourage you to actually go through and do the rest of the packet right now in class. What you don't finish in class will be for homework. Thanks, ladies. Have a good day.